The night sky. Countless stars and the majestic sweep of the Milky Way. But beyond our local neighborhood, across the cosmos, there are over 2 trillion more galaxies.
When we first began to observe galaxies, we collected them like butterflies. Little by little, we realized that they formed a web.
The cosmic web is the infrastructure that connects every corner of the universe.
You don't know anything about our universe if you don't understand the cosmic web.
It feeds galaxies, it forms galaxies, it is made of galaxies.
It's the architect of everything, and our cosmic future depends on it.
The cosmic web is one of the most important parts of our universe. It plays a key role in the evolution of the cosmos.
Without the cosmic web, there would be no stars, no planets. Nowhere in the universe where the conditions of life could exist.
How did the universe go from a hot soup of gas to a cosmic web sprinkled with galaxies, planets, and us? The universe may appear random. 2 trillion galaxies spread across the cosmos. But in this cosmic chaos, scientists detect order.
When we first saw that the universe was full of galaxies, it seemed like overwhelming chaos, but it's not. They are all connected.
Galaxies link up in a gigantic cosmic network spanning the entire universe. How this pattern emerged may be cosmology's biggest puzzle.
In some senses, you don't understand something unless you understand how it comes into existence and how it's formed. And galaxies are the basic building block of our universe.
To solve this mystery, scientists need to go deep, to the very edge of the observable universe, and study light from the first galaxies. Chile, 2021. Scientists point the VLT, or Very Large Telescope, towards the Hubble Ultra Deep Field. It's a patch of sky famously photographed by the Hubble Space Telescope in 1995. The VLT's power allows astronomers to see much deeper into space.
There's a reason people had posters of the Hubble Deep Field up in their dorm rooms in college. This was something that actually changed our view of the entire universe. I mean, I'm getting goosebumps just thinking about it. A tiny little part of the sky that we thought was empty and dark actually contained thousands of galaxies, each galaxy billions of stars. All of a sudden, the universe became that much more rich in an instant, in a single image.
Perched high on a plateau of the Atacama Desert, the VLT sees deeper into our cosmic past, collecting light that has traveled much further than the light the Hubble telescope saw. The ultra deep field is only a small section of the original deep field, but it contains secrets of the origins of galactic structure.
Imagine you take a grain of sand and you put it on your fingertip and you hold your arm out like this and you block a part of the sky looking at that grain of sand. That's the size of the Hubble Ultra Deep Field, and yet it contains thousands of galaxies in it.
The telescope stares at those galaxies for 155 hours and picks up the faintest of glows. Ancient hydrogen gas concentrated along a strand of space 15 million light years long. The filaments are just one tiny section of the cosmic web, the largest known structure in the universe.
The scale of the cosmic web is enormous. It is, by definition, the largest thing that we can see in our universe.
Today, the cosmic web is a lattice of filaments, linked streams of hydrogen gas that form an intergalactic network spanning the entire universe.
Inside the nodes of the cosmic web, you'll find galaxies, stars, black holes. Along the filaments, you'll find gas that connects these nodes, and the gas will connect to the other galaxies and clusters of galaxies. It's this beautiful superhighway of large cities that are connected through these filaments.
We can see the cosmic web about as far back as we can look. And really, galaxies are forming along that web all the way back.
This cosmic infrastructure dates back to the earliest days of the universe. 13.8 billion years ago, the universe ignites in a tiny ball of super hot energy. It expands and begins to cool. Energy transforms into primitive subatomic particles of matter. The heat from the Big Bang is so intense, gravity is effectively powerless.
The very early universe was super hot, super energetic, and regular particles of matter were zipping around so fast that not even gravity could hold them together. But regular matter wasn't the only thing in the early universe.
In the background, gravity is working on something else. Regular matter's ghostly cousin, the invisible substance known today as dark matter. It makes up about 85% of all the matter created in the early universe.
Normal matter and dark matter both existed around the time of the Big Bang, but the way they played out was very different.
Just 10 seconds after the Big Bang, the infant universe is billions of degrees Fahrenheit. Still far too hot for regular matter particles to clump together. But dark matter plays by different rules.
Dark matter isn't affected by the Big Bang's intense radiation in the same way that regular matter is. And so because it's able to cool, it clumps together in a way that regular matter doesn't.
As dark matter clumps grow, they exert a gravitational pull and begin to form shadowy structures.
As soon as the dark matter gets a foothold, we have a place where there's a bit more stuff. Then that attracts more and more dark matter.
380,000 years after the Big Bang, the intense heat drops to a few thousand degrees. Normal particles of matter move around more slowly. Protons and electrons bind together and form atoms of hydrogen and helium gas. Then, gravity from dark matter starts to work on regular matter.
Before you know it, you have this very clumpy universe with these huge dark matter halos that can now start to draw in also ordinary matter in the form of gas.
A billion-year building project begins. The dark matter clumps pull in clouds of gas. The foundations of the cosmic web and the galaxies.
Just as when you build a building, there's a lot of work that happens before the building goes up. Our universe spent a lot of time laying the groundwork for this cosmic web before it switched on the lights.
The foundations are complete, but the job isn't finished. How did those clouds of gas transform into the greatest structure in the universe? The secretive dark matter that brought the gas together is also on site, managing the build.
It was really the dark matter that called the shots in cosmic clustering, because it outweighed the ordinary stuff by a big factor.
In essence, the cosmic web is made of dark matter. Tendrils of material are stretched out across the cosmos.
As the sprawling structure builds, its gravitational pull strengthens, pulling in more dark matter. The clumps begin to collapse and shrink down into filaments. These meet at even more tightly packed clusters, creating a huge, dark scaffold that drags in more hydrogen gas.
Imagine drops of dew on a spider web. That's like hydrogen blobs being pulled into dark matter's cosmic web.
After tens of millions of years of construction, strands of gas stretch across the cosmos. Fast forward to now. the web appears in all its star-spangled glory, lit up with galaxies.
We know at some point stars and galaxies formed. The big question is when. What were the first galaxies like? That's a big mystery.
So, how then did the lights of the cosmos switch on? Evidence suggests that as the universe assembled its web of dark matter and hydrogen gas, the biggest stars that have ever lived set the cosmos ablaze. 2018, scientists study an ancient galaxy, the catchily named MACS 1149-JD1. There, they find some of the oldest stars ever detected.
This particular galaxy is exciting because it's forming stars just a very short time after the Big Bang.
Those stars could hold clues as to how the cosmic web that supports the universe first lit up. But as astronomers study starlight from when the universe was just 250 million years old, they get a shock. The stars are not just made up of hydrogen and helium produced in the Big Bang. They also contain what astronomers call metals.
Metals in astronomy is everything heavier than hydrogen and helium.
No matter where it is on the periodic table, if you're not hydrogen or helium, you are a metal, even though that makes no sense. If I were king of astronomy, metals is right out.
The Big Bang only made hydrogen and helium. Anything heavier than that was churned up in the cores of dying stars.
The bright stars of this ancient galaxy, dating back to just 250 million years after the Big Bang, contain chemicals that were created in even earlier stars.
Some of them seem to be nearly the age of the universe, extremely old, and yet they contain elements that guarantee they can't have been the first generation. As old as these stars are, there must have been something that came before.
The earlier first generation of stars remains cloaked in mystery. How did the first stars ignite? And did they kickstart the formation of the first galaxies?
It sounds like a classic creation myth. It's out of the darkness, out of nothing, structure arrived, and from that structure, the galaxies, the lights in the universe turned on.
We've never seen a first-generation star, but physicists have a theory of how they formed and what they were like. Let's step even further back in time, to around 100 million years after the Big Bang. The early cosmic web is dark. There are no stars to illuminate it. But the universe is ready for stellar ignition. Cooled down after millions of years of expansion, the gas clouds clinging to the dark matter scaffold begin to contract. As the hydrogen gas clumps together, larger clouds form super-dense, ultra-hot cores.
If you can bring hydrogen together and actually get it hot and dense enough, hydrogen will begin to fuse into helium. There'll be a nuclear fusion reaction going on.
Simulations suggest that some gas clouds are hundreds of times the mass of the sun. The stars they produce are unlike anything that exists today.
So the stars around us today really top out at masses between, let's say, 70 to 100 times the mass of our sun. There's nothing larger than that.
These first stars were up to 1,000 times more massive than the sun. So if you plopped it in our solar system, it would extend all the way past Jupiter. So think about that. That is incredibly big. That scale is mind-blowing.
So what happened to these stellar behemoths?
The lifetime of a star has a lot to do with its mass. The more massive a star is, the more gravity crushes the interior up to high temperatures, and it burns through its nuclear fuel even faster. So, incredibly, the more mass there is, the shorter a lifetime you get for a star.
The first generation of stars are sort of like the rappers and rock stars of the universe. They live fast, they die young.
First-generation stars didn't live long enough to form complex galaxies, but they did set the process in motion. The lives of the first stars may have been rock and roll, but their explosive deaths in supernovas pumped the universe full of heavy metal.
In the galaxy today, we see a supernova maybe every couple of years, close to us every couple of decades. This must have been a fireworks show. Giant supernovas going off all the time, all around you.
That act of destruction is actually an act of creation. What a star does in its core is it creates heavier elements from lighter elements.
That first generation of stars must have been absolutely incredible. Simply exploding so quickly and unloading all of this wonderful new chemistry into the galaxy.
200 million years after the Big Bang, the remains of the first stars flood the interstellar medium with heavier elements like carbon, oxygen, silicon, and iron. Crucial ingredients for the next wave of stars.
It's such a beautiful story because suddenly the whole process of star formation changed, and it literally became easier to make a star.
Heavy elements suck heat out of the surrounding gas. Cooler clouds crunch down much faster. The smaller, second-generation stars form rapidly and in much greater numbers. Somehow, this mess of stars transformed into a network of young galaxies. But it wasn't easy, because as these baby galaxies formed, a breed of matter-hungry monsters appeared in the young cosmic web. 13.6 billion years ago, the dark scaffold that supports all the regular matter in the universe emerges, ablaze with stars. But how did this stellar array evolve into a structure littered with organized galaxies? It seems they formed under constant threat of destruction. October 2020, astronomers discover a monster lurking among the cosmic web's earliest structures, dating to 900 million years after the Big Bang, a supermassive black hole. 6 galaxies surround this cosmic giant, caught in its grip, seemingly linked to the supermassive black hole by filaments of the developing cosmic web.
It's like the universe has given supermassive black holes an umbilical cord.
It's like an all-you-can-eat buffet right there.
Supermassive black holes are hungry beasts. They feast on any matter that gets too close to them.
Supermassive black holes are likely some of the most powerful objects in the universe. They can be anywhere between 100,000 to 10 billion times the mass of the sun.
Supermassive black holes have been a nemesis for generations of scientists, not because of their fearsome nature, but because nobody knows how they grew so large so early.
I wish I knew where supermassive black holes came from. If I knew, I would have a Nobel Prize hanging around my neck, and I would wear it every single day.
As someone who deeply loves supermassive black holes, whose career is based on studying supermassive black holes, it is very frustrating to not know where they come from.
Regular stellar black holes are the collapsed cores of dead stars, ranging from 3 to thousands of solar masses. But supermassive black holes, those are a different beast. 13 billion years ago, not enough stars had lived and died to build something as huge as a supermassive black hole. Now, the cosmic web offers scientists clues about the black hole conundrum. We now know supermassive black holes grow among the lattice of the young cosmic web, gorging on the hydrogen gas that travels along the filaments. At the same time, When the cosmic web is lighting up, supermassive black holes appear to be stealing star fuel from the young universe. You might think that would kill a growing galaxy. And yet, most mature galaxies have a supermassive black hole.
They really dominate the physics of what happens in the centers of galaxies, and even how galaxies can evolve.
We think these galactic monsters have been around from the start. How then did the web's young galaxies develop around supermassive black holes? The Milky Way's supermassive black hole is called Sagittarius A star. It's around 27 million miles wide and weighs in at just over 4 million solar masses.
The environment around Sagittarius A star is very dynamic. It can actually be a really hellish place. There's this accretion disk that's full of plasma, it's heated to thousands of degrees. So you wouldn't necessarily think that that's a great place for star formation to happen.
But that's exactly where astronomers decided to look. Using the Atacama Large Millimeter Array, or ALMA for short, scientists scanned the heart of the Milky Way for dense cores of gas and dust, stellar embryos. They found more than 800 within just 1,000 light years of Sagittarius A star, including more than 40 embryos with energetic jets blasting from their cores, the telltale sign of the birth of stars.
It's really surprising to find those stars there. It's like hearing babies' cries from a wolf's den.
It's not the place you would expect this to happen, but in fact, stars are forming there. Now, it's not as efficient as it is out here in the suburbs where things are quieter, but it works.
Baby stars igniting and thriving around a supermassive black hole, the kind of hostile environment we know existed in the young cosmic web. Star birth is a key part of kickstarting young galaxies. This evidence suggests that star formation is more resilient than researchers thought. And they've developed a theory to explain it. Gas and dust race around the black hole in the accretion disk. Heated to incredible temperatures, plumes of gas break off and blast into space. The gas rapidly cools, collapses, and forms baby stars. These accretion disks are the most chaotic of stellar nurseries.
You see this mechanism that you think is violently inhibiting star formation, and at the same time it's triggering the birth of new stars.
Matter clumps at the cosmic web's intersections, feeding the supermassive black holes. Around them, stars burst into life, slowly building galaxies. This could be how our own Milky Way formed among the filaments of the young cosmic web. But new research suggests that growth in these baby galaxies requires murder and mayhem, and without them, we wouldn't exist. The infant universe is a dramatic place. Stars ignite and stars die, even in the violent surroundings of supermassive black holes. Baby galaxies form with the cosmic web. But how do they grow? Scientists believe the critical factor is galactic turmoil.
The universe does need to churn things up. You need to break some eggs to make an omelet. You need to introduce some chaos into your galaxy to rapidly form stars or grow black holes.
Smashing things together is how the universe came to be.
The Hubble Space Telescope discovers many distorted galaxies, twisted, battered, and torn, victims of violent collisions on a cosmic scale.
Galaxies are never sitting quietly doing nothing. They're always undergoing change. They're constantly encountering and slamming into and colliding with and mixing with other galaxies.
You can see images in Hubble of total car wrecks of galaxies that are trying to merge with each other.
We know that galaxies collide now. But what about in the early universe, when the cosmic web was beginning to take shape? Astronomers study a strange galaxy named Himiko, born just 800 million years after the Big Bang. 3 bright light sources suggest intense star formation. Detailed analysis reveals not one galaxy, but 3 baby galaxies, not yet fully formed. Scientists call these youthful star systems proto-galaxies. The trio that make up Himiko are in mid-collision. Computer simulations of the early universe suggest proto-galaxies smash together with frightening regularity. These violent shakeups trigger starbirth.
Protogalaxies are rich in gas, and when they collide and merge, those gas clouds collide and collapse and form stars, sometimes at prodigious rates. And after 1 billion years or so, all of that structure forms and you get a formal galaxy.
Picture the early universe, 500 million years after the Big Bang. It's smaller and more compact than today. Cosmic collisions are common.
Imagine taking a bunch of cars and just letting them drive around in Nevada where there's nothing but space, right? You're not going to get too many collisions. Now squeeze them into a tiny little city block someplace and you're just going to have accidents everywhere. Well, it's the same thing with the universe. When the universe was younger, it was smaller, and these protogalaxies were everywhere. It was crowded. You were bound to get collisions between them back then.
More and more baby galaxies form at the growing web's gas-rich intersections. A collision between small protogalaxies might trigger modest amounts of star formation when regions of dense matter come together. But a merger involving proto-galaxies with rich reserves of gas can rev up the rate of stellar ignition, supercharging a growing galaxy.
Gas-rich mergers can generate star-burst galaxies, where we see incredibly vigorous events of star formation.
You might think that any trace of the original galaxies would be destroyed in the crash, but scientists pick over the remains of these cosmic train wrecks. By analyzing the crash scene, they can piece together the collisions, blow by blow. They've even done it in our own galaxy.
We think that our very own home galaxy of the Milky Way almost certainly experienced several of these galactic collisions in its past. We can learn this by looking at stars in the Milky Way, and we can figure out that some of them are moving at different orbits, some of them are made of different elements, and that gives us the clue that our Milky Way has experienced this series of mergers over the course of its history.
Astronomers think one such smash-up around 10 billion years ago kick-started the growth of the Milky Way. A group of stars called the Gaia Enceladus cluster in the outer reaches of the galaxy behaves strangely compared to other stars around it.
The stars in the Gaia Enceladus cluster, they're different. They move differently. They act different. They're like kids from the next town over showing up at your school. You just know that they don't belong. The Milky Way had already largely formed. And then this massive cluster comes screaming in. It was a violent event that eventually ended up absorbing the stars from this cluster into the body of the Milky Way itself. Galaxies are built from these kinds of collisions.
Less than 1 billion years after the Big Bang, the dark scaffold of the cosmic web begins to glow. Matter channeled down the web's tendrils creates dense clumps of gas. Even in the turbulent neighborhoods of supermassive black holes, stars burst into life. Baby galaxies collide, and the young universe sparkles with light. But an important question remains. In the mayhem of the early universe, how did galaxies like our Milky Way survive and thrive?
Galaxy evolution is very dynamic. Our understanding of galaxy evolution is very dynamic, and there's so much that we still don't know. There's a lot of different competing theories right now as to how galaxies grew into the galaxies that we see today. It's a huge open question and is something that's a big deal in science right now.
New research suggests that life and death in the cradle of the universe lay within the cosmic web. 13.6 billion years ago, a proto-galaxy, the infant Milky Way, forms in the tendrils of the young cosmic web. Today, it bears the scars of many collisions. Each one could have torn it apart. So what controls if a young galaxy lives or dies? May 2020. Scientists image a graceful galaxy that existed just 1.4 billion years after the Big Bang. Analysis of its light shows this is a starburst galaxy, pumping out newborn stars.
Galaxies like our Milky Way are old and rather stately, and they don't form stars very rapidly, about the equivalent of the mass of the sun every year. Well, starburst galaxies, yeah, they form them a lot more quickly, hundreds of solar masses per year. But BRI 13350417, 4,650 times the mass of the sun every year. It is blasting out stars.
Some young galaxies in the early universe appear to be supercharged with star fuel. How can they grow at such an incredible pace? Scientists think the answer lies in the mysterious substance that's controlled the flow of gas since the beginning. The dark structure whose tendrils stitch the universe together. But exploring this cosmic network is no easy task. When it comes to dark matter, we're flying blind. May 2021. An international team of researchers investigates dark matter in the local universe by observing its effect on the path of light. Gravity affects light. A massive object causes light to curve through space, even if that object is invisible, like dark matter.
We can't see the dark matter directly, but we can see what it's doing to the light. It's stretching it, it's bending it, it's creating arcs in ways that would never happen unless the dark matter were there.
Using an AI program, the team analyzes 100 million visible galaxies, looking for warped galactic light. Because the model is artificially intelligent, it gets better and better at finding dark matter.
What's very clever about this kind of algorithm is that it's learning as it goes. It uses the information that it has to predict the existence of new structures.
As the model teaches itself to see the dark matter behind the stars, it maps out new, dark structures, never before seen highways between galaxies.
There's a lot more filaments, there's a lot more intricacies, there's a lot more cosmic web there than what meets the eye. It's like, if you look how Manhattan is connected to the land around it, you can see all the bridges, but now we're also seeing the underwater tunnels.
The new layout of dark matter reveals the local universe is a bird's nest of hidden channels feeding galaxies with gas. Galactic structures seem to thrive at the cosmic web's most densely knotted intersections.
Because multiple filaments are intersecting in those locations, and that is a location of very enhanced gravity relative to other locations, then material will be drawn in. So these galaxy clusters are likely feeding off the cosmic web.
This connectivity could be the key to the rapidly forming galaxies in the early universe. But there's a catch.
Sitting right at the densest regions of the cosmic web can be really good for galaxy growth. You have all of this gas being funneled in for new star formation, But being that plugged into the network isn't all good news.
There is evidence that though the cosmic web gives life, it can also take life away. Scientists studying some of the universe's most heavily connected galaxies found something unexpected: plummeting rates of star birth.
In some ways, it's a little bit counterintuitive, right? If these nodes are meeting grounds for all of this gas, right? Why aren't you forming more stars there?
One explanation: in the all-you-can-eat buffet of the cosmic web's matter-rich junctions, a young galaxy might overindulge. As the cosmic web funnels more matter towards a junction and its growing galaxies, the gas influx doesn't just boost star formation. It fattens up the supermassive black hole at the galaxy's core. For a young galaxy, that's dangerous, because when this monster overeats, it produces high-energy jets and belches out super hot wind.
These black holes radiate tremendous amounts of energy when they grow, and that radiation can slam into the material around them in the galaxy and blow it all out of the galaxy, launch it away, or heat it up to super high temperatures.
Star formation requires stuff. So if you blow that stuff away, how are you going to form a star?
And what's left behind would be what we call a quenched galaxy that basically can't form any new stars.
The researchers found that although connectivity within the cosmic web can boost galactic growth, it was the superconnected galaxies that died the quickest, choked and stunted like overwatered plants. Perhaps our Milky Way got lucky.
You could say that the Milky Way galaxy is sort of in this Goldilocks zone of galaxy formation. It's been receiving enough gas over time that it's been able to keep up with its star formation, but not so much gas that its central black hole has been fed enough that it would clear the galaxy out of gas.
The cosmic web determined if galaxies lived or died. Its construction project brought order to chaos.
The cosmic web is the architect, the engineer, the builder, the construction worker, even the interior designer of the cosmos.
But now, work is shut down. An invisible force threatens to tear apart the very fabric of the cosmic web. What does this mean for galaxies and for us? The cosmic web brought order to the early universe. The gravitational attraction of its dark scaffolding helped build galaxies and fueled their development. But growth tops out at the level of galaxy clusters. Nothing bigger will ever form.
Something has stopped the formation of structure in our universe.
To understand what's going on, we need to return to the Big Bang and the formation of the cosmic web. 13.8 billion years ago, the universe sparks into life. A tiny ball of pure energy cools and expands. The energy transforms into regular matter and dark matter. But another force appears at the same time: dark energy.
Dark energy, as far as we understand it, which is not much, has always been here. It's always been a part of the universe, but it's been silent, in the background.
Dark energy is everywhere. It's over here, it's over there, it's between you and me. It's absolutely everywhere.
One theory is that dark energy never formed, that it's just a constant in the laws of physics. It has always been there and always will be.
Some physicists believe that dark energy is simply the force of emptiness.
People used to take for granted that space was empty, vacuum. But the discovery of dark energy has made some people wonder if space is actually more of a substance, and that space also might have pressure that causes things to push apart. So, yeah, whatever space is, it might be more interesting than we thought.
Dark matter dominates the young universe. But as the dark scaffold of the cosmic web grows, it sows the seeds of self-destruction. As the network of matter takes shape, pockets of emptiness form between the filaments, cosmic voids. In these expanding, hollow spaces, dark energy grows.
The weirdest thing about dark energy is that it has constant density. Constant density means the more volume you have, the more dark energy you have. So the larger the voids get, the more dark energy they contain.
Dark energy pushes against the cosmic web, opening up huge chasms in the architecture of the universe. 5 billion years ago, dark matter's strength of attraction is finally overwhelmed. Like bridge cables in a hurricane, the cosmic web's filaments stretch and snap, and the universe's substructure fails. Galactic construction freezes as the universe expands, but darker times are ahead for the cosmic web.
As time goes on, not only is it expanding, but this expansion gets faster and faster and faster.
As the dark energy in the voids increases, the entire structure of the cosmic web begins to break up.
The effects of dark energy will get stronger and stronger with time until the very fabric of space-time gets torn apart.
This isn't a superhero movie. The bad guy wins.
The future of the cosmic web is looking bleak. Ultimately, it's going to be a cold, lonely universe.
Our closest galaxies will accelerate away until they're just tiny pinpricks of light. Then, the universe will go dark again.
Everything will fade out. So the universe started with a bang, but it will die with a whisper.
The cosmic web transformed the universe from a hot mess to a sparkling structure. It gave birth to billions of galaxies and us. Without it, space would be a much less interesting place.
This giant structure, the largest thing that we know of in the universe, is responsible for nourishing the galaxies, creating the stars, making the conditions right to form life. We would not be here talking right now if it were not for this cosmic web.
Understanding the cosmic web is understanding dark matter, is understanding dark energy, is understanding our past, is understanding our future.
Really, everything that we know about how the universe works is directly tied to the cosmic web.
It's amazing to think that the overall structure of the universe that we witness today began in the earliest times of the universe and has yielded beings like ourselves who can now discover it and ponder about its existence. That's pretty dope.